Hello, my name is Kanchan Vaikar, and I work for AWS Marketplace for Machine Learning Group at AWS. And it's my pleasure to host Nick Erickson, a senior data scientist from AWS Deep Engine Science team, and also one of the authors of AutoGluon-Tabular Algorithm. The topic of today's discussion is the AutoGluon-Tabular and AutoML algorithm from AWS Marketplace that can be used to solve a variety of binary classification, multi-class classification, and regression type of machine learning problems. Here is a quick overview of today's agenda. First, we will take a look at AWS Marketplace and explore three different types of products that you can use for your machine learning needs. Then, Nick will dive deep into the algorithm itself and share different aspects such as internal workings of the algorithm, as well as benchmarking results against other popular AutoML frameworks. Then, I will show you how to quickly train ML models using AutoGluon-Tabular algorithm. And finally, I will share some resources available for you. AWS Marketplace is a curated digital software catalog that simplifies the discovery, purchase, and deployment of third-party software. It contains SageMaker-compatible machine learning models and algorithms, and a large selection of dataset products. More than 50 different partners such as Intel AI, H2O, 9, TIBCO Data Science, as well as open source framework teams such as AutoGluon have listed their models and algorithms in AWS Marketplace. There are domain-specific as well as domain-independent algorithms and models. Before we dive deep into the algorithm itself, let me shed some light on how AWS Marketplace helps you protect your data via different mechanisms. Amazon SageMaker encrypts algorithm artifacts, model artifacts, and other system artifacts in transit and at rest, and it isolates the deployed algorithm and model artifacts from the internet access, helping you secure your data. Requests to the Amazon SageMaker API happen over a secure SSL connection. Amazon SageMaker performs static and dynamic scans of all the algorithms and models for vulnerabilities to help you secure your data. Apart from IAM policies that you can define, you can further restrict which marketplace listings can be procured by your organization via private marketplace feature. And you can use AWS Service Catalog to enable certain teams within your organization to deploy allowed marketplace products. Now let us take a look at the big picture problem. Your machine learning journey always starts with a machine learning problem. First, you decide whether you want to build or buy a solution. It is not a good idea to build a solution from scratch every time you come across an ML problem. There are certain problems which have been well studied, for example, speech recognition. And many of these problems require a lot of highly skilled resources as well as time. Sometimes, before investing money in highly skilled resources and ML projects, you want to do quick POCs to show your management the art of possible. You need some quick results in matter of days instead of months. AWS offers many AI services which you can use, and AWS Marketplace offers many third-party machine learning models that can be directly deployed with Amazon SageMaker. There is a huge selection of ready-to-use machine learning models in AWS Marketplace that directly solve a business problem. There are domain-specific as well as domain-independent machine learning models. And many a times, not all data you have might be of good quality. It is important to identify and use only good quality data for training your ML model. For example, Background noise classifier can be used to identify whether an audio file contains background noise or not. When you train an ML model, during the feature engineering step, you would identify and create multiple features that you can specify during the training. And often the data is available in heterogeneous formats, such as audio, video, images. However, this data can make an important additional feature that feeds into your ML model training job. AWS Marketplace contains several machine learning models that can be used to create additional such features based on your requirements. And trying these ML models is really easy. Many ML models have try before you buy feature, which you can use to try these products without even subscribing to them. It's as simple as these three steps shown on the screen. You go to AWS Marketplace, you search for the ML model you want to try, and then choose Try Product Demo. And then you choose Upload Image and upload an image you want to perform inference on. And you will see prediction rendered on the screen within a matter of seconds. You can see here that I uploaded an image of a scientist and the PPE detection ML model returned a response in seconds. You can see that the scientist is wearing a coat, glasses, and is not wearing a mask. Now let's go back to our flowchart. Sometimes you might find an ML model in AWS Marketplace that needs to be tweaked specially for you. For example, you want the hard hat detector machine learning model to also return the color of the hard hat. Well, if you need such a customization, just leave some feedback on the listing and AWS Marketplace team can help you out. However, if you have in-house expertise as well as time and resources at hand, you might prefer training a custom ML model yourself. And for developing that ML model, you require data. If you don't have the data you need, you can procure it from AWS Data Exchange. AWS released AWS Data Exchange in November 2019, and it contains over 2,000 data product listings. Once subscribed, the data gets delivered into your S3 bucket. And once it becomes part of your data lake, you can use tools you generally use and perform analysis on it. You can also use this data for training custom machine learning models. Once you have the data, you perform various steps to identify, cleanse, and feature engineer your data, and then you get ready to train your custom ML model. You can use Amazon SageMaker Studio, or you can use analytics platform that you have been using from AWS Marketplace. AWS Marketplace also contains algorithms from popular vendors such as H2O, Intel, TIBCO, as well as frameworks such as AutoGluon that you can use with Amazon SageMaker. The experience of using algorithms from AWS Marketplace is very much like as that of built-in algorithms, but with a few caveats. You need to subscribe to the algorithm before you run a model training job. And to help you secure your data, Amazon SageMaker launches the Docker container in a network isolated mode, which means the container itself has no internet access. And you can launch it in your VPC, and you can also monitor your flow logs. Now I'm going to hand over the presentation to Nick, who will cover some background on AutoGluon-Tabular algorithm, benchmarking results, and internal workings of the algorithm itself. Nick, over to you.
Thank you, Kanchan. Hi, everyone. I'm Nick Erickson. I'm a senior data scientist at Amazon and co-author of AutoGluon. So today I'm very excited to talk to you about AutoGluon-Tabular. So AutoGluon is an open source AutoML framework built by AWS, which enables easy to use and easy to extend AutoML. It enables users to automatically utilize state-of-the-art ML techniques without expertise and achieve state-of-the-art prediction accuracy on tabular datasets in the AutoML domain. And today I'm specifically talking about AutoGluon-Tabular. However, we do have computer vision and natural language processing tasks as well. So the interesting thing about AutoGluon-Tabular is that it does a lot more than cache. And cache is the combined algorithm and hyperparameter selection problem with the intuition on relying on strategies that win prediction modeling contests. And I'll get more into what cache is and what the previous AutoML systems do shortly. So first, let's talk about the domain that we're trying to solve. We're talking about supervised learning. So in this scenario, we have input training data with the correct labels we want to learn to predict. And the output data will be the model which can, or the output will be the model which can generate predictions on new data. So it's fairly straightforward in that you have examples of something that you want to have the model learn, and then basically then it learns to predict, is this a dog, is this a cat, etc., or how much is this house worth, and so on. So solving supervised learning problems with AutoML. So what are AutoML algorithms? So often with machine learning, you need to know a lot of things going in. You need to know how to prepare your data. You need to know how to generate features and how to select and train the proper machine learning models as well as tune them. This is a very complicated process, and it's a very high bar to entry for somebody to reap the benefits of machine learning. So what AutoML is intended for is for people who just want to get a solution straight out of the gate without needing to know all the techniques that are going on behind the scenes to make it happen. So existing AutoML frameworks include a variety such as SageMaker Autopilot, AutoWeka, AutoScaler, Teapot, H2O, many others. And virtually all prior AutoML implementation approaches said that AutoML is essentially cache. Basically, given a set of machine learning algorithms and a bunch of hyperparameters for each of them, just keep training models and trying to find the particular combination of algorithm and hyperparameters that give you the best result. However, AutoGluon does something completely different. So I'm actually going to lead with benchmarking results for AutoGluon so that you can kind of understand just how differently AutoGluon approaches things. So I'm benchmarking on the OpenML AutoML benchmark of 39 tabular datasets, which is generally the standard in AutoML. AutoGluon significantly outperforms tuned light GBM models and other popular AutoML frameworks. For example, compared to AutoScaler and Teapot, which are very popular AutoML frameworks, AutoGluon achieves a lower predictive error on at least 82% of the datasets and produces between 14 and 21% fewer relative errors. So for more details and comparison on that, please see the AutoGluon paper. I should mention that AutoGluon is fully open source and that you can look at all of the source code on GitHub. And then with AutoGluon-Tabular versus tuned light GBM, AutoGluon achieves lower predictive error on 36 or 92% of the datasets and produces 27.7% fewer relative errors on the test data. So what this means is that, if you get a light GBM model with 80% accuracy and you just replace that with AutoGluon with no changes, you would expect AutoGluon to achieve about 85.5% accuracy based off of this benchmark on average. That's a huge improvement. I mean, you're removing about a fourth of the errors that you get, and with no real change to the work that you've put in, right? And models were trained on just a single 4-core CPU with a 4-hour time limit, very easily obtainable hardware nowadays. So even if you just have like, an old laptop, you could install AutoGluon on it, or use, fairly cheap instances on AWS Marketplace. You don't need to have a massive GPU instance. So how does AutoGluon relate to AutoML? How does AutoGluon make this happen? So to obtain these results, AutoGluon did not, unlike all of the other AutoML systems, AutoGluon did not hyperparameter tune. AutoGluon used the same hyperparameters for every problem, and used not only the same hyperparameters, but the factory default hyperparameters for all of its models. This goes completely contrary to nearly all well-known practices applied to machine learning. I mean, when you generally take your introductory machine learning courses, or even like all the way through your master's degree, you're generally taught that hyperparameter tuning is very important. That there are various ways of doing hyperparameter tuning, but the fact of the matter is we found a way to avoid all of that, which I'll be sharing. So let's first talk about the benefits typically gained from hyperparameter tuning. So there are a variety of different ways to do hyperparameter tuning, such as grid search, random search, and Bayesian search, or in Bayesian optimization, sorry. And the idea being that each model has several hyperparameter values, or basically levers that you can change the values of to change how the model interacts or how it trains. And based off of these levers, you can change kind of the end result or the end accuracy. Now, this is helpful in practice, or sorry, this is theoretically helpful. However, oftentimes it suffers from a lot of limitations, such as requiring many repeated model trainings with subpar hyperparameters. So even the state-of-the-art Bayesian optimization methods aren't really that much better than random search. And random search, I mean, it's in the name, it's probably not the greatest. So when you have a lot of hyperparameters, you're going to be using a lot of suboptimal settings, and it's just going to take a lot of time. And additionally, most models being trained are thrown away and don't contribute to the final result, again, because they have poor results. And a more subtle reason is that the more hyperparameter tuning done, is the more the final models overfit on the validation data, because every time you train a model, you need to check how good it is, right? You need to say, is this better than the other models that I've trained? And you can't do that on the test data, like the thing that you finally want to get the best score on, because that would just completely overfit. So you need something called validation data, which is a common term in machine learning, which is basically taking a held out set from your training set and not using that during training, but checking that during validation. The problem is the more times you check that, the more overfit your model gets, the more you're kind of lying or like tricking yourself into thinking that a model's good, because by chance, a model might be good like randomly, but it might not be good on the test data. And so there are ways to combat this, like cross-validation, but this makes the tuning process that's already long even longer. And finally, and most interestingly, it's less helpful when the model being tuned is part of a model ensemble. So let's talk a little bit about ensembles. So random forests are famously simple models which perform well in tabular settings. It's very hard actually to beat a random forest with methods developed prior to it. And even deep neural networks in tabular settings still to this day generally don't beat random forests. And the random forest is extremely simple. It's a result of averaged the predictions of many decision tree models. And decision tree models are basically, you look at the data, and for each feature, you try to split the data left to right, basically, to get the biggest difference in terms of the labels of the two groups. And then you just keep making splits to maximize the difference until you get your final like branch of decisions which end up making your final prediction. So they're very, very simple models. However, the decision tree models in random forests are purposely made to be poor models with high variance with each other, and that we do that by training on a random subsample of the data on purpose. Again, we're purposely making the models poor. And this technique builds the foundation for very, very powerful gradient boosting models that are very famous, such as XGBoost, LightGBM, and CapBoost. So let's show a practical example of this and why random forests are so powerful. So imagine that you have data like this, and the lighter the color of the dot, the higher the value, and we want to predict the color of the dot essentially, given the X and Y axis points. So this is what a decision tree would look like. Basically, it will make harsh decision bounds along the features, and this visualizes it actually. And you can see to the right, the color of the boxes, that's the value that it would predict given a new dot in those locations. So as you can see, this looks fairly decent, but obviously it's not perfect because there's some pretty severe differences in color between adjacent boxes, right? You wouldn't really want that. And again, the idea behind a random forest is you have a bunch of these decision trees. So we have a bunch of random subpar models. And then what we do is we simply average them. And now those harsh decision bounds are gone. Those, obvious suboptimal, like harsh boundaries are now these smooth transitions. And it's very obvious to see the random forest is much stronger. And what's very interesting about this is that not only is the random forest stronger than the decision trees, it's stronger than the best decision tree. And what I mean by that is if you hyperparameter tuned a decision tree and you gave yourself infinite time, you would never realistically make a decision tree which is better than the random forest because you would eventually overfit. And also because the random forest benefits from basically variance cancellation. So what do I mean by that? All of these decision trees are poor models, but they're poor models in random directions. So when I say random directions, I mean that they aren't biased towards a particular reason for being bad in the sense of like they are overconfident in a certain value and such. And what this means is that if you average a bunch of them, the reasons why they're bad kind of cancel each other out, right? Because a decision tree can be bad in one direction, and then another decision tree model can be bad in the opposite direction of that. And then when you average them, they cancel out. So that's like the intuition behind why random forest is so powerful. And so the lessons learned here is that many models are better than few generally. And models that learn differently can boost accuracy, even if they are worse in isolation. And most importantly, hyperparameter tuning to find the best single model does not necessarily help find the best combination of models. So let's talk a little bit more about ensembling. Let's talk about very complex ensembles. So we talked about random forests, right? But actually, let's extend this idea, right? So we had many decision tree models that, when averaged together in some way, created a model that's more powerful than any of them individually. But these don't have to be decision tree models. These can be any models. So let's talk about maybe the most famous case of a massive ensemble. So the Netflix prize is a competition that ran for 5 years with a grand prize of $1 million. And in order to win the competition, which was to improve Netflix's recommendation algorithm by 10%, entire new techniques had to be developed across the years. And the most famous of them is multi-layer stack ensembling. And what this produces is hundreds of predictive models which basically work together in order to make a prediction. They feed their inputs into each other. And it's a very massive effort in order to build all of this from scratch, which is why when the Netflix engineers looked at the winning solutions and to make the decision of if they want to use it in production, they decided not to, because orchestrating all this logic of these multi-layer stack ensembles was just too much effort for them. So in this sense, we would call this a monster ensemble. This is what, if you took the best scientists in the world and you gave them months and months to work on a problem, and the only thing that you cared about was accuracy, this is what they would create for you, right? This is the best you could get. This is the state of the art. So the question is, can we take that state of the art accuracy, that incredible algorithmic power, and can we tame it? Can we make them reliably performant, stable, and sensible to countless different data sets, assemble them in an appropriate manner without need for expert knowledge from the user? Can we train them in a reasonable amount of time on a wide variety of hardware, enable flexibility to satisfy user constraints, and hide complexity behind an elegant API? So with that, let's talk about AutoGluon-Tabular and how we try to attain those goals. So AutoGluon-Tabular does more than cache. It relies on strategies that win prediction modeling contests on sites such as Kaggle through multi-layer stack ensembling. It is the only AutoML system that implements multi-layer stack ensembling, and this is a hugely influential feature in AutoGluon. We also do automatic model selection, architecture search, and data processing. And we have a greater emphasis on modern deep learning techniques such as deep neural networks than most other AutoML systems. We do techniques such as repeated k-fold bagging with auto-fold prediction generation to ensure that we don't overfit. And we require no manual data preprocessing. What that means is that if you have a CSV file or just raw data in Excel, you can just throw that at AutoGluon pretty much, and you don't need to clean up the data really or anything like that, so long as it's a valid tabular data set. AutoGluon will try to handle everything as best as it can, and generally speaking, it will do a very good job, especially compared to somebody who is new to machine learning, who, if you were using like a XGBoost model, you'd have to do some kind of one-hot encoding of categoricals. AutoGluon does all of that for you, and often in ways that are more memory efficient and result in better accuracy. So AutoGluon is made for production applications. AutoGluon is used in a variety of areas inside Amazon and outside of it. And AutoGluon expects individual models training may fail and gracefully skips the next model in such cases. What this means is that as so long as like one of the models that AutoGluon trains succeeds, it won't crash on you. AutoGluon is memory aware and ensures that trained models do not exceed the memory resources available to it. This allows AutoGluon to extend on much larger data sets with less memory than most other AutoML frameworks. And again, these things are covered in our paper in depth if you want to see exactly how often AutoGluon succeeds on these data sets in comparison to other frameworks. AutoGluon also estimates future memory usage of individual models and skips memory-hungry ones such as k-nearest neighbors if it's determined that there won't be enough system memory for the training. In terms of training efficiency and time management, the user can decide how long the algorithm will train. Once the time has elapsed, AutoGluon is ready for prediction. No need to have machine learning knowledge to know that certain models will train for certain amounts of time and that how many epochs or how many trials of HPO you need. Don't worry about any of that. You just say, I want my model done in 4 hours. And then you go to the gym, take a sip of coffee, do your errands, come back, and in 4 hours, AutoGluon's ready to go. And then you can deploy that and start making inferences. It divides allocated time among models and early substantial base models once a lot of time is up. And it utilizes almost every model trained with multi-layer stack ensembling unlike HPO-focused AutoML frameworks, which again throw away the vast majority of their trained models. AutoGluon uses those models for something bigger. So how does it work? So let's first talk about tabular data format. So it's the most prevalent type of data in business. So each raw value is either a string or a number, and it's extremely diverse source of data with numerical, categorical, dates, etc. And even though there's a lot of talk nowadays about things like computer vision and natural language processing, those are actually less diverse, right? Because you don't have things like numeric, categorical dates and such. You just kind of have one known image type or one known data type for the most part in those scenarios. Whereas with this, you have many different types. And not only that, but they can mean very, very different things depending on the context, which is very hard to determine. So as an example here with month, this is a value between 1 and 12, but how does a machine learning algorithm automatically know that 12 is closer to 1 than it is to 7 in this case, right? It's a cyclical feature. And that makes things very complicated. And, you know, there are a lot of feature engineering techniques within AutoGluon to automatically detect those kinds of scenarios. So for supervised learning problem types, we have classification and regression. Classification would be like predicting the type of sale or the condition where it's just one of several values. And regression would be like predicting the price or the year of something, where it could be any number of values and it's numerical. So AutoGluon applies machine learning for you. All you do is call the fit, which preprocesses the raw data, which identifies the type of each feature, identifies the problem type from the data. Again, because you specify the column here that you want to predict, AutoGluon can just very simply take a look at that and determine for you, is this classification or regression? And then it splits the data appropriately. You have no need to specify a validation set with AutoGluon. It'll do it internally. And then it trains various base models and creates an optimized ensemble that outperforms all the individual models. One additional note that I'll just mention real quickly is that AutoGluon does offer state-of-the-art hyperparameter optimization functionality with Bayesian optimization-based hyperband, but this will not be discussed in this talk. So AutoGluon applies feature engineering. So we have global preprocessing and model-specific preprocessing stages. We infer the feature type, we discard non-predictive features, then we transform date and time features into appropriate features for use in machine learning models. For text, we even have text support actually, where we automatically send them through count vectorization models, which generate n-gram features. And we treat missing categoricals and new test time categories as unknowns. So what this means is that if you have missing values in your data, these are infamously difficult and challenging things to deal with, especially for a newcomer in machine learning. Dealing with missing values can very often lead to severe defects in your system. However, AutoGluon has robust handling of missing features and missing values, such that you don't need to worry about that in your data. So in terms of model-specific preprocessing, AutoGluon implements data skewness correction through its neural networks, missing value imputation through random forest, k-nearest neighbors, and neural networks, and many more, which will go beyond the scope of this talk. So if you want to learn more about the preprocessing techniques within AutoGluon, feel free to reference our documentation. So we use a variety of algorithms within AutoGluon for our models, including random forests, which was previously discussed, extremely randomized trees, k-nearest neighbors, custom neural network implemented using MXNet-Gluon, and powerful boosted trees, including LightGBM and CapBoost. And it's fair to note here that LightGM and CapBoost are very commonly the best individual models, but the other models add useful diversity to the ensemble. Remember before when I was talking about the decision trees, poor models that are different in how they learn when ensembled together are more powerful than any individually. So let's talk a little bit about the exact ensembling technique. So we ensemble through cross-validation folds and bagging. So think of your data, think of your test data as something completely out of the scope of this slide for the most part, except at the very bottom. And let's talk about your training data. So you do not send AutoGluon validation data, instead AutoGluon determines the validation data itself. How it does this is that it will train multiple models of the same type with the same hyperparameters, just with different sets of the training, different subsamples of the training data. So here, let's talk about a 5-fold cross-validation case with bagging. The idea being that you split your data into 5 20% chunks, and then for each model, you take 4 of those chunks and use those as training and 1 as validation for like things like early stopping. And so therefore you train 5 models in this sense. And now there's a very subtle trick here that enables very powerful multi-layer stacking functionality. Notice on the right-hand side, after training these 5 models, you now have validation scores and predictions. You now have validation predictions for every row in your training data. And these predictions are not overfit because they were not used during training. What this means is that you've essentially created a feature, but it wasn't you that did it. It was the machine learning model. Again, your data, when you think about it in tabular data, it's just a set of features that are either numbers or categories, and then you have your label, right? And you just try to predict with that using the features that you have. We just created a new feature. We just created a feature which is basically, this is what this model would have predicted if it saw this example, right? And you can use that as input to another model. So this gets into the meat of things, the multi-layer stack ensembling. So a stacker model is a model which uses predictions of every base model as extra features. So you have your initial features, maybe you have 10 features, and then you train 5 base models. You have your k-nearest neighbors, you have your LightGBM, CapBoost, neural network, random forest, right? And each of these makes prediction probabilities. And because you use cross-validation with bagging, now you add all of these as additional features, and now you have 15 features. And so now when you're training your stacker model, which again is the same kinds of models, we don't actually change anything between the stackers and the base models in terms of like the hyperparameters or the models used. We use the exact same ones. And we just concatenate those predictions with the input features. And so now we're training a LightGBM that sees what a random forest sees, that sees what a neural network sees, that sees what a k-nearest neighbor sees, and it can use all that information to make an informed decision about how it wants to learn based off of the original features as well. And what this results in practice is a massive improvement in the overall predictive accuracy of the model. Unprecedentedly high improvement, such that basically every single winning solution to a Kaggle competition is a multi-layer stack ensemble. Pretty much every state-of-the-art benchmark period in machine learning for tabular data is a multi-layer stack ensemble. And what's very interesting is that even in Kaggle, they don't really hyperparameter tune these models for the most part, because the stacking component of it really just solves most of the problems on its own. And hyperparameter tuning doesn't really add too much to it, because remember, trying to find the best individual model doesn't necessarily help you find the best combination of models. And the same is true here. So hyperparameter tuning actually adds very little. And then what we do once we have our stack layer, and by the way, we can keep stacking. Now there are subtle things here in terms of overfitting that occurs if you stack too many layers, which I'm not going to get into too much here. So we generally limit it to just a couple layers in practice. But then in the final layer, we will weight all of the models using a ensemble selection technique to finally get our output predictions. So with that, I'd like to hand it over to Kanchan for now, where she can walk through a demo of AutoGluon-Tabular.
Thank you, Nick, for a great overview. What I'm going to cover now is really the end-to-end demo of AutoGluon-Tabular algorithm. Using AutoGluon-Tabular algorithm from AWS Marketplace is really easy. And the first step is to get into AWS Marketplace and then subscribe to the listing. Once you have subscribed to the listing, you will be able to use AWS console to trigger an AutoML job on your data. Once the training completes, you'll be able to deploy the model generated and perform both real-time inference as well as bash inference. Now let me switch to AWS console and show you the algorithm listing as well as usage instructions before I subscribe to the algorithm. So what I've done is I've opened AWS Marketplace, and in order to see all the dataset products, I can simply select AWS Data Exchange. But in order to see the SageMaker compatible algorithms and models, I need to select Amazon SageMaker as the delivery method. You can see that there are two types of resources, model packages and algorithms. Since we are interested in trying out AutoGluon-Tabular algorithm, I'm going to select algorithms here. You can see that there are over 80 different algorithms in AWS Marketplace from different vendors such as Intel AI, H2O, TIBCO, Sensify, and others. Now what I'm going to do is I'm going to click on this link and I'm going to actually select Amazon Web Services. And you can see that I see the AutoGluon-Tabular algorithm over here. If I click on this particular AutoGluon-Tabular algorithm, you see the AWS Marketplace listing of this particular product. You can see that the listing says that this is an AutoML type of an algorithm, which can be used for regression and classification type of ML problems. If you scroll down a little, you'll be able to see more information in the product overview section. It clearly states out here that the algorithm itself takes care of missing data, feature transformation, splitting, model selection, algorithm selection, tuning, ensembling, and everything that is required in order to automatically solve that regression or classification type of a problem. It also mentions the multi-layer stack ensembling, which Nick just covered. If you see the right-hand section, you'll see the highlights over here. And you can see that the first highlight specifically states that this particular algorithm creates models to predict values in one column based on the values in other columns available in that particular data set. It also does specific techniques in order to curb overfitting and in order to create that ensemble model for you. If you see the second highlight, here it talks about some of the benchmarking results. You can clearly see that this particular algorithm has been evaluated on a large selection of data sets, and the paper itself, the research paper itself, contains information about details of the benchmarking results as well as the experimentation performed using the AutoML data set. If you scroll down further, you'll be able to see this third highlight, which talks about the data pre-processing. It clearly states out that this particular algorithm does not need any specific data pre-processing. If you scroll down further, you'll be able to see the software pricing as well as the infrastructure pricing associated with this particular algorithm. You can see that this is a free algorithm. That is, there is no software charges associated with this algorithm. And regular SageMaker infrastructure pricing applies based on the instance type that you choose. If If I scroll down further, you'll be able to see the usage information in this particular section. You can see that for training, it accepts a text/CSV format. And if you just want to, give it a try, you can actually use this data set or the bank marketing data set from UCI in order to actually try out this particular algorithm as well. In fact, we are going to actually do that. If I scroll down further, you can see further constraints as well as additional information about the data itself that needs to feed into the algorithm. You can see that the algorithm requires minimum of 50 rows, and if you have a large data set, large number of rows or a large number of columns, it recommends you to use larger instance type. You can see that the algorithm supports a wide variety of different instance types. Under inference section, you can also see that the supported input content type is text/CSV. And similarly, the output content type is also text/CSV. Now, what do you do if you want to actually give it a try? Well, it is extremely easy to try out this particular algorithm. In fact, the AutoGluon team has also authored a sample notebook that you can directly use using your Amazon SageMaker Studio or using a notebook instance. So I'm going to click on this link, and you'll see that this is the sample Jupyter notebook, which you can actually run from end to end in order to try out this particular algorithm. You can see this particular notebook is actually using the direct marketing data set, and then it is doing a train test split, and then it is training an ML model using the Python SDK, and then it is performing real-time inference, and then it is performing batch transform job in order to do a batch inference. So we saw how this particular algorithm has several links as well as additional information that you can use in order to try out this particular algorithm. So what I'm going to do now is I want to click on continue to subscribe button. So when I click on continue to subscribe button, this is the page on which you'll be able to see both pricing as well as the end user license agreement associated with a specific algorithm or specific model. And there is an accept offer button which appears over here. So once you click on the accept offer button, a subscription will be made in your AWS account to this particular algorithm. You can see that I've already subscribed to this particular algorithm. So now I can click on continue to configuration. And you'll see that the latest version of this particular algorithm is 3.3 at the time of this recording. And this is the product ARN that I can directly specify if I want to trigger an AutoML job using the AWS console. But you can see that it goes one step further and it actually provides you this create training job option right over here. Now, before I click on that, let me actually go back to the deck and tell you a little bit more about the data before we click on that particular button. Now that you've seen what the listing looks like, what I'm going to do today is I'm going to do a quick demo using the direct marketing dataset. The dataset is a marketing dataset containing a combination of around 20 different numeric and categorical features. And the outcome column indicates whether the customer is going to accept a specific marketing offer or not. And what I've done is a 70-30 train test split on the dataset. Now let me switch to the console and quickly show you what the data looks like. So if I scroll up, you'll be able to see here that these are the different features. And this is the outcome column. Right? And you can see that these features, some of them are categorical, some of them are numeric, and you can also see the train and test split that I've done over here. I have approximately 12,356 records in the test split, and I have 28,832 records in the train split. So what I've done is I actually went ahead and I wanted to actually show you how to do this via console. So I literally, used these. So I decided to use these two files. I've downloaded them locally, and then I uploaded them into an S3 bucket. We can see that this is the train.csv, which was created using the direct marketing dataset. What I'm going to do is I'm going to click on the copy path button. And then what I'm going to do is I'm going to go back to this configuration page, right? So if you remember, we actually went ahead, subscribed to this particular algorithm. And after that, when we clicked on configure button, we came to this particular page. Now I'm going to click on, I'm going to leave this selected and I'm going to click on this particular button. So you can see that it directly takes me to the create training job screen within Amazon SageMaker. And this shows the seamless integration between AWS Marketplace and Amazon SageMaker. Now I'm just going to specify a job name such as AutoML Direct Marketing job, and then I'm going to select an execution role over here. Then I'm going to scroll down. I'm going to select a slightly larger instance type, a little more memory. Maximum runtime, I'm just going to leave it as 2. Then over here, I can actually specify the label column. You can see that in the direct marketing dataset, our label column had over here. This was a label column, right? Which is why I've left label as Y over here. And I've also specified presets. So let me actually quickly, go back to the product page and tell you a little more about the channels and the hyperparameters. So you can see that this particular AutoGluon-Tabular algorithm actually emits the validation score based on the evaluation matrix that you specify as part of the presets. So fit args is a hyperparameter which is supported by AutoGluon-Tabular. And if I open this particular link, I'll be able to see all the hyperparameters that are being supported by this particular algorithm. You can see that this particular AutoML algorithm lets you specify the amount of time for which it should execute. It lets you specify different type of presets, such as do you want to train for best quality, or do you want to train for best quality with high quality refit, or do you want to optimize for deployment? You can actually specify one or more such presets as part of the training itself. And to know more, you can check out this particular documentation. You can also see that the algorithm itself is going to identify problem type for you based on your label column. And this is the evaluation matrix which I was talking about. So over here, AutoML, this particular AutoML algorithm lets you specify one of these values that you can tell AutoGluon-Tabular algorithm to evaluate. So what I've done is I've left all of these as it is, and you can see that there are over 30 or 40 different hyperparameters that are actually supported by this particular algorithm. So I'm going to go back to the AWS console, and you can see that I've left this information as it is. I've left presets as optimized for deployment. Over here, I need to specify the S3 location. So actually, let me just go here and click on copy path and paste the S3 location over here. I'm going to leave everything as it is. I'm not going to specify. I can actually also specify the testing channel so that the algorithm itself calculates test-related matrix as well. But for now, I'm just going to leave it as it is. Then over here, I'm going to specify this as the output location. And then I can simply click on create training job in order to trigger a training job. In interest of time, I actually took the liberty of executing a training job, and you can see that I got 0.92 as the accuracy on the validation data set over here, which is a pretty good ML model, right? And you can actually see this reflected over here as well. You can actually see the different types of ML models that were trained by the AutoGluon-Tabular algorithm. And you'll be able to see the different types of matrix that it evaluated and the results that it got in this particular table as part of the logs. Then I can simply use the console in order to either stand up an endpoint, or I can just simply trigger a batch transform job. So here is a batch transform job that I triggered using the console. I specified the test file, that we had created a little bit earlier. And this is the output I got. You can also see the output directly by going to this particular location. So if I click on this particular location, I'll actually get a file that I can download and I can see the detailed results for my test data set. And based on the results, you can actually calculate and see what kind of test matrix you get as well. But shortcut is really to directly use a sample notebook provided right over here. Just a second. Yeah, right over here and try it out via a Jupyter. And that really completes the visual part of the demo that I wanted to quickly show you. Now, just a quick recap. I just showed you how I was able to use AutoGluon-Tabular algorithm from console. And to summarize, AWS Marketplace contains multiple such purpose-built algorithms such as AutoGluon-Tabular for your AutoML classification and regression type of use cases. And then these algorithms can be used via a standard Amazon SageMaker interface without you having to learn a new language just to use it. AWS Marketplace deploys these algorithms in a container that is network isolated, which means the container itself has no internet access. And thus, it helps you secure your workloads. You can also launch these in your custom VPC and monitor flow logs. With AutoGluon-Tabular, you get around the experimentation process. Typically, as Nick mentioned, as a data scientist, you would try different algorithms, neural nets, GPMs, and others, and try different combinations of hyperparameters to see which algorithms give you the best outcome. AutoGluon-Tabular not only does all these steps, but it also goes one step further by creating an ensemble model that incorporates all these ML models that were trained. The algorithm itself is built for you. If you are a developer who wants to train production-grade models, you can use this algorithm with your data, and it will take care of converting categorical features, text features in the numerical format for you, and it will do much more in order to ensure that it is able to train a good quality model for you. And if you are a data scientist who want to go one step forward and actually adjust over 40 different hyperparameter knobs that I just showed you, well, with this algorithm, you can. If you want to know more, I definitely would recommend you to check out this particular research paper. And AutoGluon itself is open source. And here is the website that you can check out in order to know more. Now, Nick, can you tell us a little more about how to contribute to the open source version?
Yeah, definitely. Thanks, Kanchan. So what I would just like to emphasize again is that AutoGluon is fully open source, Apache 2 licensed, and what we're really looking for is to democratize machine learning for people who, don't necessarily have all the skills needed in order to succeed in model building and data preprocessing such. We want AutoML and AutoGluon in particular to ease that process, to make it simple and easy to use to get the state-of-the-art kind of results, and to really accelerate the rate of experimentation and progress within ML. So with that, if you are interested in helping us democratize machine learning, please feel free to go to our contributing guidelines on GitHub and to contact us through the GitHub issues or through email. We'd be happy to talk more, and if you reach out, we are happy to also add you to our external contributor Slack channel as well, where we have bi-weekly meetings on advancing and brainstorming new ideas in AutoML. Thanks.
Thank you, Nick. That's great. So apart from that, I quickly wanted to also cover some of the AWS Marketplace for machine learning related resources for you. Well, there are several videos you can watch to learn more. There are several sample Jupyter notebooks that you can try. And in Spring 2020, AWS Marketplace team conducted a virtual hackathon and got some really cool project submissions. I would definitely recommend you to check out the project gallery over here. I also recommend you to try out ML models using the newly released Try Before You Buy feature. And then there are several blogs that show you how to use models, data, and algorithms from AWS Marketplace. And that really completes the presentation today. Once again, thank you so much for attending the Tech Talk. And special thanks to you, Nick, for co-presenting with us today. If you have any questions, feel free to ask in the questions panel or write to AWS Marketplace team on the email shown on the screen. Thank you.